Okay, so for this first video, we're going to show you the solution for sample problem number 1 in the module that is uploaded on your portal entitled EE424-1. So this module is actually discussing your AC meters, specifically AC meters which make use of half-wave rectification. So just to give a brief background on why there needs to be rectification when you are to implement your AC meter. So I hope you've read your module already, but cut the story short, if you're going to implement the measurement of AC or AC voltage or current, you cannot basically just make use of the D'Arson valve directly without any form of rectification in it. Why is that so? Because if, say, this is your D'Arson valve meter movement, I want you to recall what fundamentally a D'Arson valve meter movement is. So it's basically a DC motor. And if you're going to recall your DC motors, especially of this arrangement, if there is a reversal in the direction of current, then you may expect a reversal now also in the direction of the rotation of the motor. So if current, say, enters this terminal going to your D'Arson valve meter movement, it's going to produce a rotation which is opposite that when current is going to enter the other terminal. And remember also that your D'Arson valve meter movement is designed only to be unidirectional, so it must deflect at one direction only, because remember it has suspension mechanisms. So if your input is, say, sinusoidal, then that implies that it has two alternations. So it has a positive alternation, and at this positive alternation, current is now entering at this terminal. Whereas for the negative alternation, current is entering this terminal. So this is happening very quickly. So you might look at it in two ways. Number one is, since this is happening very quickly, the meter movement, or the pointer rather, is not going to be responding at any of these alternations, simply because the average value, which is what it's going to respond to anyway, is 0. The average value of a sinusoidal input is 0. It's like, since this is happening very quickly, the pointer is just going to be steady at the 0 position. So it cannot cope with the frequency, which is actually 60 hertz in the Philippines. If you say 60 hertz, you have 60 cycles. Remember, it's going to do 60 of this, 60 like this one, in 1 second. So how will the pointer respond to that? It's going to respond to the average value of that, which is basically 0. The second one is, if you're going to look at it also, there is a little bit of danger here, because if the current is coming from the opposite terminal, then the tendency is it's going to rotate in a direction which supposedly is not meant for it. So it's going to attempt to do a deflection going counter clockwise. I'm talking only of the negative alternation. So if you remove the positive alternation and only the negative alternation gets retained, it's going to be dangerous also for the meter movement. If you can recall, you have to connect your terminals properly to your DC source. So you cannot interchange those terminals. If it's doing a negative rotation, that can cause damage to your meter movement. So because of these reasons, there needs to be we need to do something in order for us to be reading a certain voltage from your input. And that is with the use of rectification. So what happens if we're now going to apply rectification? So I would assume you're done with your elec. So if you place a diode there, a diode fundamentally, if you're going to simplify it, it only has two states. So one being forward biased and the other one being reverse biased. So if you have a sinusoidal input here, one a positive alternation, the other one is a negative alternation. So for the positive alternation, let's say this is the positive alternation. So current is going to come from here. This diode is going to be forward biased. If it's forward biased, that means the resistance it's offering is it's approximately zero, right? If you look at it to be an identical diode, it's approximately equal to zero, or it means it's as if it's a short circuit. Well, that's for ideal instances, but in reality, of course, you also have a measurable forward biased resistance for this diode. So in short, it's going to allow current to pass through it. So there will be current that will pass through the meter movement as well. So it's going to respond according to the value of the input. So if the input here is very small, the response here is small also. If the input is large, it's going to be large also. And back to a small one, and back to 0. However, during the negative alternation here, so current is going to come from here. What happens is this diode is going to be reverse biased, and if it's reverse biased, technically it's now offering a very high value of resistance. And if it's very high, it's almost equivalent to an open circuit already. And if it's an open circuit, then there will be no continuity here. Or if you look at it to be very, very, very high, then the current passing through or coming from this terminal is going to be very small because of this very high resistance, because it's reverse biased. So very small current, very small deflection, approximately 0 deflection. So there is no negative deflection here. So if we continue, again, we have positive alternation. Oops, I'm sorry. I'm going to have positive alternation, and then another 0, then positive alternation again, another 0. We therefore have here a half wave rectified sinusoid. And again, of course, this meter movement is not going to respond in real time to these fluctuations. It's only going to respond to its average. So again, this is how I explain sinusoids to my other students. You can simply look at this to have an average value, imagining as if it were sand, and you're supposed to flatten that sand there. So that is now its average value. So the average value of a halfway rectified sinusoid is equal to its maximum value divided by pi. There. So which actually we had a computation in your module. I hope you have read your module already. A 10 volt RMS AC voltage is only going to be interpreted by this meter movement to be 4.5. So which now leads us to the conclusion that the AC sensitivity is only 45% of the DC sensitivity. And basically that's all you need to understand. So it's not going to be as sensitive as a DC meter. So if you're using the same meter movement, say this meter movement was designed to deflect at full scale when the input is 10 volts DC. So if you place here a 10 volt battery, it's going to deflect full scale. However, if you replace that battery with a 10 volt AC source, it's only going to deflect 45%. And this is the reason why, because we implemented half wave rectification using a single diode. There is a little bit of modification basically to clear out this negative alternation here, and we can make use of instrument rectifier, but I will discuss that in my next video. So for this video, let's just solve the example. So we have an example in your module, and let me just copy the example. So you want to compute for the value of the multiplier resistor for a 10 volt RMS AC range on the voltmeter shown in the figure below. So we need to come up here with the value of RS, the proper value of RS. So we have a diode for the single diode rectification, and this one, the meter movement. So some specifications of the meter movement were given already. And what are those? Let me check. We have the full scale value, which is 1 MA. As well as the meter movement resistance, which is 300 ohms. There. We wanted a range, we want to have a range of 10 volts RMS. So that's 10 volts AC or 10 VRMS. And that can only be done if the computation of RS is correct. Other things to consider here is that we will be taking into account a diode which probably operates ideally such that at forward biased condition there is no forward biased resistance. So it's as if it's a short circuit during the forward biased condition. So taking all of those into account, the first thing that we must keep in mind is that the parameters of the meter movement are always given in DC. When it's talking of the full scale current here, which is 1 mA, that 1 mA is a DC value. And remember also that sensitivity is the reciprocal of your full scale current. So if your full scale current is in DC, then you are now only capable of determining first your DC sensitivity and not the AC sensitivity. So the DC sensitivity here is equal to 1 divided by 1 mA. So 1 divided by 0.001, which gives us, of course, 1000. Now you might be asking, how are we supposed to solve for RS when we have not yet discussed any equation on how to solve for RS if we're talking now of AC voltmeter? And the answer there is very simple. Of course, it's the same as how you would solve your multiplier resistor if it's in DC, because they have the same design. The design has not changed. The only thing that has changed is that the sensitivity for the AC is going to be weaker. So if we're going to recall that formula, we basically have the sensitivity in DC before multiplied to the voltage will now be equal to the total resistance. As I always say, this is nothing but Ohm's law. This is just Ohm's law. Sensitivity is 1 over current, so voltage divided by current is resistance. So if we put that in AC terms, SAC multiplied to VAC range, this is now the range of your AC voltmeter, is simply equal to the total resistance of the circuit. Remember that this circuit right here is only responding, this meter movement right here is only responding at the positive alternation of the source. So this total resistance is only computed during the positive alternation. There. So applying what we know, since DC sensitivity is 1000 ohms per volt, we can now solve for the AC sensitivity. Oops. Again, I usually mess up my brush size. There. Can now solve for our AC sensitivity, which is equal to 45% of your DC sensitivity. So 45% of 1000, which is now equal to 450. Unit is still ohms per volts, but we have to emphasize that this is now volts in AC. They're applying the formula. S is 450. We need a range, or we want a range of 10. That should now be equal to the total resistance during the positive alternation. So what are the common resistances? Of course, we need the multiplier resistance, which is what we're solving for. And sometimes we also have the forward bias, the resistance of the diode. That is why I emphasized here that this must be the total resistance during the positive alternation, so that you know that if this diode is if this diode is not ideal, it means it has a forward biased resistance, then that resistance must be included here in the computation of the total resistance. However, judging from how the problem was stated or the problem was presented, it's telling us that we are going to treat this as an ideal diode. So it has zero resistance. So plus Rs plus zero, and then the last resistance which we must consider is the resistance, of course, of the meter movement. There. So the required multiplier resistance for this AC meter, AC voltmeter, is 4,500 minus 300 is 4,200. Okay? There you go.